Love it when a plan comes together. Today, the plan is coming together. We're going to take every single thing we've learned up to this point in chemistry, and we're going to shove it in one big problem. The problem is called stoichiometry, and stoichiometry is the language of chemistry. We're going to take the formulas, we're going to take the balancing equations, we're going to take the masses, we're going to take everything we know, and we're going to use that to find out what we don't know. It's a wonderful process. What you're going to need today, you're going to need yourself a periodic table, you're going to need your calculator, you will need, maybe this might help, this is what I always like to use, a fresh cup of coffee and some chill jams. You know, today I'm not going to be able to play any music probably in the background, because if I do, YouTube will shut this down and there'll just be a mute video of me just there. So as you get going on these problems, feel free to crank up the jams and make sure that that you follow along this first part. I'm going to take you through the first one, and I hope it works out. On these problems, the chemicals and the numbers and all that change, but the pattern is the same. Now, later we'll change this pattern and make it do what we want to do. But for right now, the pattern is going to be the same today. All right, so hopefully this works out for you. Pay close attention. It can be really fun. I really, most people enjoy it when we do it in class. This will be a little bit different because you're not going to have your friend there to help you out in the spots where you're lost. So let's start with looking at this problem. It says the combustion of a sample of butane, and butane is C4H10. That's lighter fluid. It's in the plastic Bic lighters, right? And what we're going to do with that is we're going to try to, let me keep on reading here, is it produces 2.46 grams of water. So what do we say it produces water? Well, it's going to burn. It's combustion, so that's fire. So butane plus oxygen forms carbon dioxide and water. So it formed 2.46 grams of water. We want to find out how many grams of butane were actually burned during the reaction. All right, see how useful this is? You know how much was made, you can now find out what it took to make that. Or vice versa, you have so much of the reactant, you can find out how much product you're going to make. It's like a recipe that allows you to change the amount of ingredients so you have a new amount of product. Pretty amazing. Not only this will help you with your chemistry, but if you love to cook, this can also help you with your cooking, which is a great thing. Okay, let me scoot down here a little bit, or let me scoot up here a little bit. There we go. No, that's not good. I'm going to stay right here. All right, so we have our pattern, and this is the pattern. I'm going to use this pattern all the time, and the pattern goes grams to moles to moles to grams. You'll hear me say that 1,000 times. Every day for the rest of the year, I will now say grams to moles to grams. Well, maybe not for the rest of the year, but for at least the rest of the semester. All right, so we'll start this off. Now, what does that mean? Notice I have it in our map form that we used in our other factor label thing, and I have a factor label table down there. So what we have now, balanced equation, factor label table, it's all starting to come together. All right, so we always start off with the grams of given. And let's see what this says. We have 2.46 grams of water. What I like to do is mark this on the paper. I think I'm going to put it in red today. So I'm going to put 2.46 grams of water. I'm just going to write it right above my map, because that way it'll be right there so I can just glance at it. I don't have to reread this problem over and over. And it wants me to know how many grams of butane are burned. So I'm going to put a little question mark above the butane, and I'm going to put a gram right here. And that will say to myself, how many grams of butane? All right, here's our pattern. Grams of given. Givens are the one they give us the number for, the amount we know. So our given in this case is water, H2O. We have 2.46 grams of given, H2O. Moles of given, that will also be H2O. Moles of unknown, what are we trying to find? The butane. Grams of unknown, what are we trying to find? The butane. You only use two formulas in this factor labeled table. You can only use two at a time. The given and what you're trying to find. All right. I'm going to, and you don't have to do this every time, but I'm going to do this right now, is I'm going to replace the word with given with H2O. Because that's what I'm given. I'm going to replace the term UK, and UK is my unknown, short for unknown, with butane. All right? And again, just to see the pattern. I want you to see this pattern on the first one. Okay, now, remember our factor label table rules. The first thing in the map goes on the top of the table. So what do we have given? We have given 2.46 grams of H2O. The labels are super important here because we have more than one chemical involved. And we want to make sure we know what the heck we're talking about at all times. Okay, with that being said, I'm going to focus now on the labels and not on the numbers. Save the numbers till later. All right, what's the next thing we want to know? We want to know how many moles of H2O. How do I know that? Because my map tells me right here how many moles of H2O. So that's what I'm looking for. All right, what's the next thing I'm trying to find? Moles of butane. Moles of C4H10. Follow the map. That's why we have a map. How many grams of butane? C4H10. Okay, oops, I'm covering that up with my picture. I know that's a pet peeve for some people. They don't like it when my picture's in front of the problem. Okay, here we go. So now, we have to cross out these labels. Remember what we do? We just crisscross this out, right? So if we have grams of H2O right here, we cross that out with grams of H2O down here. If we have moles of H2O right here, we cross that out with moles of H2O here. If we have moles of butane, you don't have to think about this. You just take what you have on the top and you cross out the next column over. And we have moles of C4H10. Okay, now my labels are complete. Now I'm going to focus on the numbers. Now, we've done this first section. If we're changing grams to moles, we already did that, right? We know what to do. We're going to change grams to moles. We have to have numbers that are equivalent. We have to have equivalent grams with equivalent moles. All right, and then Mr. Arnold says this same saying every time. If we have grams over moles or moles over grams, the moles is going to be 1, right? Focus in on 1. And the grams is the number from the periodic table, the mass from the periodic table. So this is H2O, right? H2O, and you might know that already without looking. But if we look at our periodic table, hey, hi guys, woo! All right, so we look at that, and H is right here. H is 1. We have 2 H's. Oxygen is right here. It's 16. We have one oxygen. So 2 plus 16 equals 18. And I know what you're saying. I knew what water's mass was. And so we have 18 grams of H2O, right? 1 mole is 18 grams for water. 1 mole of water has a mass of 18 grams. That's the equivalent. We'll do the mole last. Okay, we're going to the back end. We also know how to change moles into grams. That's this last section right here. We know how to do that. If we have grams over moles or moles over grams, the moles is going to be 1, and the grams is going to come from the mass from the periodic table. It's the same exact thing, except it's on its head. We have the moles on the bottom, grams on the top. That's it. So, hey, there he is again. All right, so here we go. H is 1. We have 10 H's, right? That's 10. carbon is 12. So 12 plus 10 equals 22. So we put 22 grams here. Oops, I'm sorry. I added wrong. Mr. Pullman just came in next door and I just added wrong. I got distracted. So we have 12 times 4, right? So 12 times 4 is 48. Plus 10 equals 58. So our mass, I just did it down here. So our mass is 12 times, or 4 times 12 plus 10, or 1 times 10, so 58. So 58 grams for butane. All right. Now, that's all set up. Now, everything we've done so far is what we already know how to do. There's nothing new so far at all. And that's what's great about this. When you're putting a bunch of stuff you know together, the important part is you already know all the stuff except how to put it together. And this is how we put it together. This is the big step. This is the new step. And you have to ask yourself some important questions. The most important question I'm going to ask you right now is, why did we have to balance equations? What purpose did that serve? Right? What purpose did that serve? You know, we didn't use it for anything. We just balanced it. Mr. Arnold made us balance all these equations, and we just left them. Well, guess what? Now we're going to use the balanced equation. What that balanced equation stands for is that is a ratio of moles to moles, right? So if we have 13 moles of oxygen, that means we have 8 moles of carbon dioxide. If we have 2 moles, and this is the big one, right? If we have 2 moles of butane, that means we have a ratio of 2 to 10 moles of H2O. All right, so you see what see what we did there? We have 10 moles of water per every 2 mole of butane. That's what that's for. That's called the mole ratio. And the abbreviation for mole is MOL, so that's why I just wrote that there. I didn't forget my E. So when we write mole, we write MOL. We don't write just M. That has another label already. All right, something else uses that little m later. You have to write out MOL. Okay, and now we're set up. Now this is where you need your calculator. The pattern that you follow is not as important as the following thing. What you have to do, what you have to make sure you do, is when you multiply the things on the top. So here's a pattern you can follow. 2.46 times 1, of course the 1 is optional there, times 2 times 58. As long as it's on the top, put a multiplying sign, a times sign in front of it. And then if it's on the bottom, you don't have to worry about parentheses or anything like that. Just put a divide sign in the calculator before it. So you're going to put in divided by 18, divided by 10. And you can put divided by 1, but you don't need to do that. So in my calculator for realsies this time, and I'm not putting in the ones. And you can do this in any pattern. You can try a different pattern if you don't believe me. 2.46 times 2 times 58 divided by 18 divided by 10 equals. And my answer that I just got was 1. Oops, I'm in a highlighter. 1.585 grams of C4H10. That's it. But Mr. Arnold, that was just 25 steps. Yeah, I know, there's a lot of steps. You have to follow the steps. You have to do the steps in pretty much order. The process is not hard. You just have to follow the map, write the formulas, do all those things that we have done all year, and it should work out just fine. All right? Yeah, you know what? Just be happy that I didn't make you balance the equation that time, right? Look for the joy in little things in life. Hey, we didn't have to balance. Yay! We didn't have to write all the formulas. Yay! We could have. We still can. But let's focus on just putting this together this way. All right, so what I'm going to do is I am going to silently, I don't know about silently, but I'm going to work out a few more problems for you. Let's see how she works out. Okay. And I'm just going to go at my normal speed. So buckle up, I guess. I don't know if that's the right word, but we'll get it going here. Hopefully you can see this. I know I get in trouble if I block those things I'm writing. I'm sure there's going to be little cartoons running around here. Well, this is actually playing, but let's see what happens. Okay, so calculate how many grams of iron can be found from 16.5 grams of iron 3 oxide. I know that's iron 3 oxide because I can look at that and I can calculate that the charge of the iron had to be +3, right? So let's go purple today. So we had iron 3 oxide, 16.5 grams. That's our given. So our given is iron 3 oxide. So we have 16.5 grams of Fe2O3, right? By the following equation. I'm sorry, calculate how many grams of iron. So grams of iron, grams of Fe is our unknown. Let me start this all over. I'll delete that middle section, okay? Okay, here we go. We're ready to start this problem. And how many grams of iron? How many grams of iron? So we're looking at how many grams of iron. Why does he keep repeating that? Because how many grams of iron is our unknown? That's what we're trying to find. So I'm going to put a question mark, grams, above Fe. Can be made from 16.5 grams of iron 3 oxide. So Fe2O3. By the following equation. So our given would be 16.5 grams of Fe2O3, iron 3 oxide. Oops. So there's what we have so far. Did I say I was going to write this above the balanced equation? I think I probably did. All right, let's put it here. Okay. All right, so that's what I have. The given grams, and I'm trying to find grams of iron. Okay, let's start with our given grams. So our given is going to be 16.5 grams Fe2O3, right? And we might as well put in our unknown right now. Our unknown is grams of Fe. All right, now the given symbol is iron 3 oxide, Fe2O3. So our given, our moles of given, so we're trying to find moles of Fe2O3. Our moles of unknown, our unknown was Fe, so moles of Fe. There's our pattern. Grams of Fe2O3, moles of Fe2O3. Notice they're the same because they're both the given. Moles of Fe, unknown. Grams Fe, unknown. Fe is our unknown. The only unknown. Fe2O3 is the only given. Don't use any other symbols in this problem. That's what we have given. That's what we're trying to find. Don't start mashing everything in there because you think you should. You can only do one thing at a time, and that's find this given to that unknown. All right, here we go. So we're going to cross out grams of Fe2O3, cross out moles of Fe2O3, cross out moles of Fe. You're saying, Mr. Arnold, you didn't even think about that. That's right, you don't have to think. All you're doing is crisscrossing those out. You're canceling them out, right? Same symbol, same unit. Unit symbol, same. We're just taking it down a notch. All right, now we have to find the numbers. If you have grams over moles, moles over grams, the moles is going to be 1. And the mass comes from the periodic table. So we have Fe2O3. There's Fe right there. So we have 56. And I have a calculator here in my hand, right? And so we have 56 times 2 plus 16. So how do you know it was 16? 16 right there. 16 times 3 equals 160. Okay? So what do we have? We have 160 grams of Fe2O3. Hey, let's skip it and go to the end. What did we say that mass of Fe was? I think I said it was 56 already, right? So 56 there. And 1 mole. How do you know 1 mole? Because 1 mole of Fe has a mass of 56 grams. 1 mole of Fe2O3 has a mass of 160 grams, all right? That's the definition of a mole. It's the mass, the atomic mass units in grams. All right, now we're to our mole-mole step, or our mole ratio. This is where you need the balanced equation. Make sure you get the right number with the right symbol. Right here, Fe2O3 has an invisible 1 in front of it. So this Fe2O3 moles is going to have a 1 right there. This Fe has a 2 in front of it. So this Fe moles down here is going to have a 2 in front of it. The mole ratio comes from the balanced equation. Okay, now it's time to punch this into the calculator. Right? I'm going to switch the pattern up. Why? Because I can. So we have 16.5 divided by 160. Remember, if it's on the bottom, just put a divide sign in front of it. Times 2 times 56 equals 11.5. Grams of iron. Problem 2 done. Okay? Same pattern, totally different numbers, right? You're just following that pattern. You have to change the pattern. It's not like you can do the same exact thing every time. You have to think a little bit, but not all that much. Okay, what do we have going on here? All right. Position yourself, correct. Iodine chloride can be made from the following reaction between iodine, notice it's diatomic, potassium iodate, and hydrochloric acid. Hydrochloric acid is the HCl, all right? Remember the acids start with H, right? Calculate how many grams of iodine are needed to prepare the 28.6 grams of the iodine chloride. Okay? So I'm going to mark on this balanced equation what I know. How many grams of iodine? Unknown. Let's go this brown color, right? How many grams of iodine? So here's iodine grams. All right? So we're trying to find that. Are needed to prepare 28.6 grams of this. 28.6 grams. 28.6 grams. Okay, I think we're ready. So we're going to go from grams to moles to moles to grams, right? Our given is going to be ICl. Our unknown is going to be I2. All right? So there's our pattern. I'm on 2 screens here at once. Let's see if I can shrink this down so I can actually see the numbers. I need to see the numbers while I do it. There we go. Okay. Let me slide over to the side. Let me try this one more time. Hey, there we go. Okay. So here we're at this now. So we start with our givens. So we have, now it's really small and I can hardly see it. Let me make it a little bigger. So we have, I know, high maintenance today, huh? 28.6 grams of ICl. Right? From here on out, follow your pattern. Right? Follow the pattern. Cross out. Follow the pattern. Find our numbers. Okay? If you have grams over moles or moles over grams, the moles is 1. Hey, let's take care of that 2 at a time. And the grams comes from the mass in the periodic table. Hey, there I see, let me scoot down just a little bit. I see Cl and I both at the same time. 19 and 127. So 19 plus 127 equals 146. Okay, let's look at I. I was 127, but it's I2 because it's diatomic, right? So when it's in that last form, it's not just 1, it's 2. So 127 times 2. 254. Okay, now we're ready for our math. I'm just following, let's use, I just go by column here. So we have 28.6 divided by 146 times, whoopsie, Mr. Arnold, you didn't put in your mole ratio yet. Let's pause, let's go back. All right, I2. I forgot, I don't usually leave that to last. I'm just doing that for you guys. So we have 2 I2s. Where are you getting that number? I'm getting that number right up here. Look at that balanced equation. So the 2 goes with the I2, and a 5 is going to go with ICl. Make sure you get them with the right things. 2 and 5. They're with the correct, right? That's important. They're with their correct formula from that balanced equation. Okay, so now I'm ready. So I already put in 28.6 divided by 146, right? Times 2 divided by 5 times 254 equals, I have 19.9. And that's grams of I2. All right. Now, get back here on screen. Let me get my face here in the middle. All right, that will give us number 7. I know the numbers are not in order, but that's not important, is it? No, I've erased a few of those out of there to make it doable. So there's 2 more problems. All right, follow those patterns. I tell you what, I will get you semi-started on what we're calling number 7, just by making sure everything gets in the right spot. I'm going to go, let's see, this nice green color. Okay. All right, so they're talking about the reaction here. You read through this, but you're looking for how many grams are given and then what you're trying to find. That's what you're looking for. So when you read, look for the important things. The nitrite ion in potassium nitrite is changed into nitrate ion by the action of potassium permanganate in sulfuric acid solution. How many grams? There it is. How many grams? Did you see that? How many grams of KMnO4, potassium permanganate, are needed to carry out this reaction on 11.4 grams of potassium nitrite? There they are. Given unknown. All right. Oops, the green screen went off the screen. All right. So you see that? So I will put this stuff above my balanced equation because that's a good habit. It's nice. It makes it, it makes it easy to see. So make sure you get things where they're supposed to be. Right? Once you get in the right spot, you won't have to read that problem again because it's right there on that balanced equation. And we're trying to find the potassium permanganate. So we're trying to find this. All right? And the beauty of this type of problem, it doesn't matter if it's the reactant or it's the product. It works on if you have something given amount and you want to find something else, you can find it. All right, I will put the first thing down for you, 11.4 grams KNO2 moles KNO2. It's hard to do this when I don't know where you're at on the problem-wise, right? So I'm just, in class, I would probably do a little bit less each time. I'm just going to leave you one complete one to do. How's that? And then we're trying to find our unknown moles of KMNO4 grams KMNO4. All right? What are you going to do next? Right? Cross out your symbols and your units. Cross them out. Don't write numbers yet. Cross them out. Come on. Come on. Cross them out right now. Okay, here we go. Now, grams over moles, moles over grams, moles, 1, grams, the mass from the table. Right? Look them up. Put a 1 with the moles first, right? You can do both. You can do both. You can do here and you can do down here, right? Now, find that mass and put it with the right spot. Put it where it goes, with the grams. Mass goes with the grams, not the moles, with the grams. Okay, add them up. You got to find them both, all right? If you haven't found it yet, pause for a second. Okay, now, our last step, that mole-mole ratio. Look at the balanced equation. You can see enough of it from the side of the screen over here, right? And put those numbers in the right spot, right? Match them up with their symbols. Now your time to put in the calculator. Multiply the top. Start with your 11.4. 11.4 divided by, it's on the bottom, divide, top, multiply. All right, I'm going to quit talking and then write down your answer. Okay? Answers will pop up in the real video right now. I don't know what the answer is, so. All right, last problem. Right, you do the same thing. It looks like I need a subscript there. It changed fonts. I had to switch it over to Google, and then I had to switch it over. So, that's supposed to be a subscript. Here and here. Yeah, I don't know what happened there. So one of the format changes. It's fine here, though. Okay, so start with your things you know. Chief component in glass is silica, which is the formula of SiO2. It can be used. Silica is dissolved in hydrofluoric acid, that's HF, according to the following reaction that produces silicon tetrafluoride, SiF4, a gas at room temperature. How many grams of SiF4 can be produced? Here it is. Here it is. This whole last sentence is the money shot, right? How many grams of that from how many grams of this, right? Given, unknown. All right? And that's all I'm going to leave you on this one, okay? It shouldn't be too hard. I got to quit talking. This has been over 30 minutes already. Okay. So good luck with these. I will have an answer. The answer's probably popping up somewhere. Maybe I'll have it pop up right over here, right here. Answer right there. Okay. And so this isn't going away. You can't fake these. You can't fake chemistry. You got to know the steps. And good luck with these. Hopefully this won't take a very long for this chapter because we're not really learning anything new. We're just putting things together. So good luck with it. Of course, I do have my Zoom classroom that's open. It's only open up during regular school hours, not at 1 o'clock at night, not, no. And, so if you want help, if you can't get it, check out the Zoom room. Maybe text me, right? Send a remind to me. Hey, Mr. Arnold, I'm in this Zoom room, and you're not in here. Of course, I'm not going to be in there by myself all day. So if I'm not standing right by my computer, throw me a text, and we'll jump on Zoom, and we'll hash these out. Hey, have a great day. Again, remember, a little bit of coffee. Crank up the jams and just relax and follow those patterns. It's really fun. Usually in class, this is some people's favorite thing to do. So on your own, it may not seem so favorite. Okay, hey, have a great evening.